Okay, in our second example, we're going to be looking at the nitration of aromatics. And so this is an electrophilic aromatic substitution reaction. And we know that the nitronium ion is going to be the electrophile. And this is a high energy electrophile, so it's a very reactive species. Our aromatic is going to be the nucleophile. And the electron density from the nucleophile is going to attack the electrophile. And so we can think about how this is going to take place. Where we start to form the carbon-nitrogen bond, and we start to open the oxygen-nitrogen pi bond. And so if we do this, what's going to happen to the development of charge? And so we're going to start to develop some positive charge in the aromatic and some negative charge on the oxygen where we're breaking the pi bond. And this will leave us in a charged balanced state. So we can draw this transition state such as this, where we've put our X in the para position from the electrophile. And if we do that, we can utilize any lone pair that might be on X, and we can start to push electron density towards the development of that positive charge. And this would tell us that if X was an electron donating group, this should greatly speed up the reaction. And if we think about the product of the reaction, again, if we have X in the para position, we can delocalize the fully formed positive charge that we can put in the ortho position. Again, if that X group has a lone pair, if it's electron donating, we can draw a resonance structure where the negative charge is delocalized onto X. And of course, this would be a highly stabilizing resonance structure. So when can this happen? So this can happen if X equals a methoxy naming our two good electron donating groups. Okay, so let's think about the effect of the substituent on the nitration of substituted aromatics, the electrophilic aromatic substitution reaction. And so we know in this reaction, our transition state structure is going to have significant positive charge formed in the aromatic ring, and that the product of the reaction is going to be the substitution product where we have substituted a hydrogen for the nitro group. And so we know, we've already seen, that electron donating groups will stabilize the transition state structure significantly, and electron withdrawing groups will destabilize the transition state structure. So if we make our Hammett plot, and again we're going to look at rate constants for the rate determining step. So log kx over kh, those are little k's, those are the rate constants. Electron donating groups on the left, electron withdrawing groups on the right. And so what is our slope going to be? It is going to be very steep and negative. And we can see that in this case, the rho value equals negative 6.4. So this is a very large rho value. And that, of course, is because the substituent is going to be able to interact with the positive charge very significantly, with the electron donating groups speeding up the reaction and electron withdrawing groups slowing down the reaction. And the difference in the rate constants between these two types of substituents will be very significant, and that leads to a large rho value, in this case with a negative sign.